Okay, so this presentation will be dedicated to the Kautex pilots. My colleague Thanasis and I, and of course, UPC and FIT have participated during this pilot. So we will be offering an overview of the process. First, we will start showing what we are actually doing for this pilot, which problem are we solving, and we will show some kind of context about this business, Kautex. Then we will switch to the first tool, decision support framework, that third we'll introduce, and then we will show the model building, labeling, and recommendation. Lately, we will finish showing some of the impacts that we are causing for this pilot. So let's jump to the video. It's really small. Okay.
Hello, my name is Heino Gerens and I'm working for Kautex Textron. Before I'll start to explain about our pilot project, I'd like to present you in short who Kautex Textron actually is and what we do. Kautex is part of the Textron Group, which is a multi-industry company that was founded in 1923. Textron is known around the world for its powerful brands of aircraft, defense, and industrial products that provide customers with groundbreaking technologies, innovative solutions, and first-class services. Over 35,000 employees are working worldwide in many different businesses that are grouped in 5 segments. Kautex places itself in the industrial segment and represents about 16% of the total Textron revenues. Kautex is positioned globally to be able to support in both product development and manufacturing from the Americas to Europe and Asia. With our headquarters in Bonn, Germany, Kautex operates over 30 plants in 14 countries, always in close proximity to our customers. Besides our product locations, we also have 9 engineering, research and development locations around the world. This next video was created some years ago, and although the blow molding technology shown in the video is not identical to the processes we are running for our pilot, it will give you a good insight on that part of the manufacturing process our pilot focuses on.
As the pioneer of plastic blow molding technology, Kautex continues as the industry leader, building some of the world's most advanced and efficient automotive tanks. The construction of the SCR tank systems and plastic fuel tank, or PFT system, begins with blow molding. The different manufacturing lines are set up and programmed depending on the tank in the production that day. For the SCR tank, it's a single layer molding process and a 6-layer molding process for the PFT system. Kautex tanks begin with polyethylene and a blend of other materials. Arriving by train or truck, these materials are a key component to the manufacturing process. Tough and durable, the polyethylene is fed into the hopper, where it is heated, pressurized, and extruded into the accumulator or co-extrusion head. Once the head is full, it pushes out the heated plastic. Captured between 2 molds, the plastic is injected with pressurized air, and the blown shell is formed. The tank flashing is trimmed and the excess material is fed into a grinder where it will be recycled and reused in the molding process. The tank is then weighed to ensure quality standards are met. Once the weight is confirmed, the product receives a digitally etched identification code or serial number along with a time and date stamp. The barcode serial number will be scanned throughout the manufacturing process. If the shell doesn't meet specifications, it is removed from the conveyor belt and scrapped, or sent to the quality lab for investigation.
The knowlEdge pilot runs in our production plant in Belgium. This plant was founded in 1991, and we currently employ 120 people that run 3 production lines in a 3-shift pattern, 6 days a week. Our turnover in 2023 was about $60 million. We deliver an average 2,200 parts a day to 3 different customers. Over the past 32 years, we have supplied fuel tanks to more than 12 car manufacturers worldwide. The production line that our pilot is focused on is producing parts of Volvo's scalable platform. The blow molding process we are using on this line is a NGFS2 process, which is more complex than the process that was shown in the video. This complexity is needed due to the EU emission regulations. To ensure product quality and stability, we continuously monitor more than 2,000 parameters, and this alone in a blow molding machine. And that's why we decided to be engaged in the knowlEdge project. Our objective, together with the other members of the consortium, was to develop an enhanced anomaly detection system, which is capable of monitoring a high number of variables from different types of equipment and quality resources. We expect the system to be able to continuously monitor these multiple data sources and to identify between the different features of process, equipment, and quality information. In addition, we thought about a graphical user interface to alert the user at the production line of any anomalies that occur, both in real time or with the option to look back in historical data. The user interface should also allow the user to provide feedback on their findings or their actions. This information should be used to train the system. The system should then be able to identify similar anomalies in the future and propose a resolution based on the historical data. The capabilities of the knowlEdge platform will be presented by the technical partners themselves. I hope you enjoy the rest of your day and I'd like to thank you for your interest.
Can I start?
Sure.
So, hi all. I am Thanasis Kotsiopoulos, a colleague with Alexandros from CERT, and I'm going to present you a demo for the Kautex case about our decision support framework. During the short time, and because we wanted to fully explore the functionalities of the decision support framework, the data specialist view is employed. And the scenario of this demo is, first of all, for the data specialist to understand and observe if any anomalies are detected during a shift. And of course, apart from the anomalies identified, also the data specialist is going to explore and see any deviations in the AI model's performance and also get notifications about the technical KPIs that are derived by the AI models. So let's bring it up. The objectives of this presentation is, first of all, to demonstrate the assistance of a decision support framework for anomaly detection processes in order to enhance the process efficiency. Apart from this, we want to showcase the ability to create anomaly reports. We need the domain expert to verify that this is an anomaly and also maybe provide a direct cause of this anomaly, associate the anomalies provided by the model with the anomalies that already exist that are real. And of course, we want to utilize the causal logic recommender that Alexander showed to you previously in order to identify any underlying patterns in the data and understand the root cause of anomalies. The execution steps of this demo. We have the data specialist that will enter the DSF and will go for the live data visualization view to observe the anomalies. Afterward, the specialist is going to register an event, and then he will visit the historical data visualization in which he can find all the events in the event logger or the anomaly reports that he or she has generated. And of course, visualize each feature, each machine value basically for a specific time range. Afterwards, he or she will navigate to the AI analytics view in order to observe anomalies identified for a specific time range. And he will continue by exploring the explainable AI techniques and visualizations that you have created in order to understand what features has the most impact in order for the model to generate its verdict. And then we will explore the notifications and recommendations generated for the user, and also how the user can monitor the KPIs over a shift. So basically, this is the landing page of the decision support framework. From here, the user can navigate in every view of the system. Here, the data are first presented in a tabular format. This was the user requirements for this case. And then he has also the option to select the chart format in order to start observe the actual values of every feature that participates in the data set, and also group the anomalies with all the available models. Now, for example, we are working with the anomaly transformer. When the data specialist clicks on an anomalous point, he has the ability, as I told you before, to inject his knowledge and categorize an anomaly based on his knowledge. Also provide here a description for the demo purposes. In the historical view, the user initially gets a notification and information basically about the datasets that participate currently in the production process. In the event log, it is possible to visualize all the anomaly reports that are generated. And apart from this, the user can also sort the reports by time or by event type or by the direct cause. Here we can see also that the previously registered event is now inserted in the event logger. And as I told you, we have also the search functionality in which we can group by the direct cause all the events that are generated by the domain expert. In the historical monitoring, based on a specific time range provided by the user, we can observe every values that are coming from the machines. The user can select all the values that participate in the production process, like the active power or the extruder heat percentage values. And then in the AI analytics and explanation view, is possible to have a list of all the available models that are already deployed in the decision support framework, and obtain the anomalies based on a specific time range and the normal values by selecting the model the user prefers. So the graphs are interactive, and you can hover in and zoom in or zoom out. And in the explanation view, by selecting a specific time range, the model, and the methodology, you can have a look at which features are selected by the model in order to predict a timestamp, a time series data as normal or anomalous. For example, here we have the supply values. The purple, the color is the more this feature is participating in the model's verdict. Sub techniques are based on game theory. And also we can use the MSA explainability technique, which is also a technique that provides which features contribute most in an aggregated format. In the recommendations, firstly, the user is possible to obtain information about the technical KPIs and the production process using the fuzzy logic. And then in the causal logic analyzer view, we can have an indication using a graph in which we can hover in and see that changing the features of changing the values of a specific feature, we can see that the cause that it will have to other features. For example, changing the values of the blow curve actual value has an indirect impact on the blow molding machine last cycle. Two methods are used for this recommender. One is graph neural networks, and the second one is the not-tiers methodology. Last but not least, in the key performance indicators view, the data specialist has the opportunity to explore and get details about each KPI that is inserted, and also visualize the KPIs for every shift. And now we can continue with your side. Thank you.
Thank you.
Thank you.
No, it's fine, don't worry. Okay, thank you, Thanasis. Okay, now we will focus on a different process: model building, labeling, and recommendation. Sounds really weird. Now we will see what we are doing here. So first, let's see the scenario. For the Kautex pilot, we are using the training cloud-based, inference fog-based pattern, which means that we use the advantages of the cloud to execute complex trainings and also to process big data. After, for executing, for example, inference processes or to access to the client data, we remain in the edge. During this process, we have different steps. So we start having the data analysis here, in which we have the purpose of building an unsupervised model. For that, we use actually manufacturing data coming from the historical data storage that before Eduardo showed. We can keep on with a domain expert labeling data. This is a way to inject expert knowledge in the system. And afterwards, this knowledge is inserted, it's inserted in the same database. In order to use all this knowledge and also to use a static quality data that is here in my corner, this is the ground truth data. We can actually use the hybrid recommender and another tool, the Edge embedded kit that we showed before, in order to build supervised models. So here the difference between the whole processes is actually the purpose and also which data we are using. Here we can see some of the tasks that we are solving. In general, we saw that is actually an anomaly detection problem. But as I said before, depending on the data that we are using, we are on the first or on the second task. So in the first one, this is an unsupervised task. We are just using manufacturing data coming from the sensors, so from the flow plant, and we are focused on trying to find some hidden patterns inside this data. Within the supervised is actually the same task, but here we are using quality data coming from also from the expert in this domain, and we perform a classification task. Also, we try to find which are the main features that are making that, like they are making some impact, I would say, sorry, in the anomaly detection. So this is a way to see which features are more important during the prediction. Here we see the 4 steps and the components that are involved in this process. So for building the models in the supervised and unsupervised task, we have first the knowledge discovery engine and the HMDA kit. When the deployment comes, we use the orchestrator. This can be executed in the cloud, edge, or fog. In the middle, we have the labeling and the recommendation. This is the case in which, for example, we are not sure about which model we can use. And in order to retrieve, in order to get the choice, we can use this recommender. After we will show some details about it. In order to have like a tracking of all the process, we save data in the AI model generation repository and also in the knowledge repo. Now we can go to each of the steps. Here in the unsupervised anomaly prediction, within the knowledge discovery engine, we can see that actually we can perform different tasks, not just anomaly detection. We can also perform clustering, feature extraction, extraction discovery. Disallowed detection is anomaly detection. So also we have some of the results that we are getting in a visual way. We have model trainings, also the cycles that we get for each feature, cycle times. How we identify these cycles, because this is an unsupervised model, so we have to validate this somehow. And then the similarity search that we will see after in the demo, just to try to see if the anomaly that we are getting is actually it already occurred in the past or not. And in the list on my left, we can see some of the models that have been implemented within the platform. In the anomaly labeling, within as well in the knowledge discovery engine, sorry, we have the chance to label, inject this expert knowledge within the system, and also to find similarities among the anomalies. After in the demo, we will see with more detail, so I will skip this part. In the third step, the recommendation, based on the type of problem that I want to solve, based on the data that I have, the list of models implemented, and also about taking into account the performance analysis of previous models, we can try to see which are the models, the best models for my case. Once we have the model, we can train it or retrain it if we have several models available in the knowledge repository. Among the problems that we can solve here, using supervised data, quality and manufacturing, we have classification, anomaly detection, and also forecasting. As an example here, we have some results about which are the most important features for our problem. Of course, this is just a little example. We have more models doing that, some training results, some clustering examples. So we have kind of really variety of models to choose. Here we can also see some of them. Now let's jump to the demo. So we will show first the labeling. So let me play it. Here we are using the knowledge discovery engine again. This is an unsupervised task. Okay. So first, what we do is to load a configuration. Now we are going to load a previous one already created, just to speed up a bit. But here the idea is to define the model, define from where I'm getting the data, if some preprocessor is needed. Here we specify if we are using the HDS. Once we have to skip the process because it takes a bit long to load. But once we launch it, we can identify the anomalies. Here we have two, the most important features involved in this prediction, some changes or weird things happening for this feature. Here we have like a dropout. And then here we can decide if this is already strange or not, mark it as anomaly, and put maybe some comments for the future. Then what we do is to jump and see, okay, which are the similar anomalies that we can have, similar to this one. Again, we load the configuration. This is really customable, so you can change it, change the sources. Then we get the results, 5 similar anomalies to this one. We can see also the time periods and how similar they are based on a distant function. Here we have the similar anomaly and the past anomaly. We can see the differences between of them changing the feature. So here, for example, we just select fit zone temperature and see that actually they look alike. But of course, this depends on the expert in the domain. And we can classify it as well as an anomaly. Then let me go to the supervised. So let's see how we connect one component with the other. So now we jump to the supervised model building. Here we can retrain or train a model. We are focused on the retraining. So we guess that we have like already one model available, already trained for anomaly detection. And what we want to do is to use the data that we previously labeled in the component. So this is a way to enrich our model injecting expert knowledge. So let's see what we do in order to launch these. Okay, so the configuration is actually the same than the other component. Let's just select the model, well, the type of problem, sorry, the model that we want to use, preprocessor, if we need one, we can have a specific preprocessor. If we have a labeler, in the Kautex case, we do have, and the action that we want to perform. Here we have to include the reference of the model and from where we are actually getting the data. If we want to put some specific time interval and specify what is the target column, because this is a supervised problem, so we need to say, okay, this is the quality data. Okay. This is already, and we are not gonna show the details of the background process, but this is just the answer of the orchestrator. The orchestrator, once received this request, start the training process and send the results through the broker. And actually, that's it. This would be the end of the overall process. Then, okay, yeah. So in the end of implementing all these tools, we try to see, okay, are we actually helping this pilot? And we observed that we made some improvements in the overall process. This is regarding the maintenance of the flow plant. Also, we saw that this helps to, in the sense of the preventive, maintenance, all the line of the machines. Here, I mean, for example, calibration, lubrication, adjustments of the machines, see when they have to be maintained. Also, this helps them to identify some changes in the machine cycles, and of course, to prevent when an anomaly may occur, because we saw that they have to stop the overall chain when they have actually an anomaly, just to identify what happened. So they are actually saving cost and time. And in addition, this help them to define, okay, if we have this set of problems, maybe we can define also a list of generic rules to apply.